Have our first midterm, and just to make a comment about that, it's going to be open notes, and that means you can bring your notes, written notes, and your homeworks and quizzes, anything you have on paper, but no books and no electronics of any kind. So, understood? And my plan going forward is that next Monday, then, the day before the midterm, I will just have that as an open class with just Q&A. So we won't be introducing any new material that day. So I'll find out if you use that, if you actually show up, and if you actually use the time for questions and answers. I'll do it again for the second midterm. If you don't, I won't. I'll just give new material going right up before the midterm. So that's the plan. Any questions about it before we just go into it? Yeah.
Is there gonna be like a line of demarcation where we're like, okay, we don't need to worry about this being on the midterm?
Mm-hmm. Yeah, it'll be right up, it'll be everything we've covered.
From
And I will give you in post tomorrow an outline of the whole course, detailed outline of the whole course up to the point of the first midterm. I'll post it in the files part of our Canvas website. Anything else? Where are we going today? Where we were was we had used the mechanism of reducing derivatives by building derivatives out of the fundamental equations and using the exactness of those equations to get a couple of very useful expressions for du and dh. So I list them there. But what about the expressions that we might have for ds? Now we can get at them by rearranging the fundamental equations to be explicit for ds. Recall we've got expressions of du is equal to tds minus tdv, and we've got dh equal to, is equal to tds plus vdp. So I can rearrange those to be explicit for ds. I can have either ds is equal to cv dt over t plus partial p with respect to t at constant v dv. Or I've got from this equation cp times dt over t minus partial v with respect to t at constant v dt. So I can now use, oh, sorry, those are my final results already. I jumped the gun on you. So let's use these things to get that down to a manageable size here. So I get ds is equal to du over t, if I can write it that way, minus p over t dv, or ds is equal to dh over t plus, it's going to be, this is going to be a plus and this will be a minus. That right. And so now we use the expressions we've got for du and dh to plug in here for these and get the final results that we want for ds, and that's what I was writing before. So ds is equal to cv dt over t plus partial p with respect to t at constant v dv, or I can write it and these are very useful equations. So here what I've got, just to summarize, I've got two useful expressions here for du and dh, and then two for ds. And those are going to be very useful. Also, let's note that these are also exact differentials. So I can use Cauchy-Riemann conditions for these as well as the original fundamental equations. So there's quite a load of information in there. Now, the next order of business is to look at the type of abstract derivative in which it is the abstract quantity which is held constant. So let's look at an example. GDP at constant H. This is the so-called Joule-Thomson coefficient, and it tells us how much the temperature changes, usually drops, as we throttle a fluid from a high pressure to a low pressure. So let's just remind ourselves of that Joule-Thomson coefficient, and it has that physical significance. We'd like to be able to express it, if we could, in terms of measurable properties. Well, if H is constant, then I can write dH is equal to 0, and then express H here as partial H with respect to T at constant P dt plus partial H with respect to P at constant T dP. And now I can rearrange this. This is at 0, so I can write dt dP out of this is just equal to minus, now just look at this, minus partial H with respect to P at constant T over partial H with respect to T at constant P. And this is all at constant H, so this thing turns into partial T with respect to P at constant H, which is what we were after. Well, now let's take a closer look at it and see what it amounts to. We've already derived both the expressions for both the numerator and the denominator in earlier work. So I can write this as, this is just C sub P, so I've got 1 over C sub P, that's the denominator. And here, remember, I've got B minus T times partial V with respect to T at constant P. So we're done. We've now reduced that abstract derivative with a quantity held constant, which is abstract, into something that can be evaluated in terms of measurable properties, which is always what I mean when I say reduced. That's what you're going to remind me of.
Oh, yeah. Yeah, right.
There you go.
How did you get that last term again?
This last one?
Yeah.
We've derived it at least a couple times already in class.
From the definition of dt
Yeah, we've
dp?
derived the expression for dH dP here at least a couple of times in class. We derived it so that we could get this. There it is. That's dH dP at constant T. And we've derived it in earlier lectures, so I don't think I need to derive that again.
And then you divided it by dh dt constant p?
Well, that's what this is. This is that derivative, and dH dt at constant P is just Cp.
Oh,
So what I'm left with here is minus
Yeah.
1 over Cp times this expression.
okay, thank you. Cool.
And so if I had an appropriate equation of state for the gas and a value for the heat capacity for that real gas, then I could evaluate this in terms of those measurable properties. So let's look in general what we did to reduce a derivative in which the abstract quantity is held constant. So the general form for that would be, let's say I have a derivative partial of y with respect to x at constant m. And I think it would be a good idea just to memorize this. It's going to be minus the ratio of the derivative of m with respect to the denominator and at constant y over the derivative of m with respect to the numerator, constant x. So there's the general form. So once you have that internalized, and as soon as you look at one of these right away, you just write down what the result is for that. And then you proceed further from there with the derivatives that you have in the numerator and denominator to reduce them if necessary.
Is that a rewording of the cyclic rule?
I have no idea what you mean by the cyclic.
Oh, that was in the book.
Okay, well.
Okay, never mind.
I can't
All right,
answer it.
yeah, I see that. Okay,
You'll have to ask Koretsky.
okay.
I like this simple way of doing it. We have 4 utterly simple rules of mathematics here that we can use to reduce these derivatives. So we don't need cyclic rules, we don't need Jacobians, we don't need a lot of these other fancy terminology that is used to carry this out. It's simpler than that. Let's look at a couple of examples of things that we've done. First one being an example of changing this abstract variable held constant. And the other one will be another important example of reducing derivatives, and then we'll move on. So example 1 is going to be, we're interested in the pressure-temperature relationship along an isentropic path. So that's, I'm writing this carefully here, isentropic, that means constant S. Oh. So what kind of process units does this correspond to? Any idea? Yeah.
Turbine?
Turbine is one of them, right, and how about another one?
Compressor.
Compressor, pump, expander. So there's a lot of different important special cases for which this characterization thermodynamically applies. So we might be interested in knowing how the pressure and temperature vary along such a path. So let's see, I've written it this way. Right away, I should be able to write that and know it's going to be minus. It'll be the ratio of S with respect to T. Constant P, that is S with respect to the denominator over derivative of S with respect to the numerator. Okay, so we've got that step. Now we look at the numerator and denominator by themselves, and these are things that we've already dealt with. This have minus, and the numerator is going to be what? That's just Cp over T. These are derivatives of S with respect to T and P. If we want to recall that, we did that right away in the class, so we can go and look at these and just pick them off. So that's Cp over T, and excuse me, the denominator is going to be T times, it's got a minus there, dV dt at constant P. So the minuses go away, and I can write this as I'm sorry, that T does not belong there. Minus does. So I end up with Cp over T times partial V with respect to T at constant P. Now you have actually, this is the general result. It would be applicable to any fluid for which I have the appropriate properties. But let's look at the case that I think you've probably seen last quarter, and that would be for perfect gases. Now for perfect gases, Cp is equal to, and for perfect I'm going to put a double star there, and that means we have a constant heat capacity. For monatomic gases, Cp would be 5 R, and for diatomic under 500 K would be 7 R. The idea is that it's a constant. And of course, for perfect gases, they're also ideal gases, so PV is equal to RT. So we can look at what our coefficient is, RdP dt at constant S. And I can write that now, as long as I'm just gonna be in a constant S environment, I'll write that as dp dt is equal to, just looking at this, evaluating these, this is gonna be CP double star up here. And down here, I have t times, now partial b with respect to t. That constant p is r over p. So I have down here RT, oops, and P up here. Such good writing. But this is all now in the environment of constant S that's implied here. So in that environment, I can just separate variables and integrate this. So I end up with dp over p is equal to cp double star over t dt over t, or integrating between an initial and a final state. I end up with log of p2 over p1 equal to cp double star over t log of t2 over t1. Or if I exponentiate it, I'll get P2 over P1 is equal to, I can pull this in and make it an exponent. And that's something that I think you've seen before. We see now that's the special case that derives from this general result that we got. Yeah.
What happened to the R?
Oh, did I leave that out? Well, there it is. Oh. Thank you. Let's look at another example, which is an important one. It's not one where we change the variable held constant, but it's one where we need to reduce derivatives. And that is the general relationship between CP and CV. Well, we can think about how we might do that, and we can feed off the equations that we have derived so far. And let's look at the expressions we've developed for ds, because they're going to involve both of those CP and CV values. So I'll flip back here. Remember these guys again? So I can equate the two expressions for ds, and I'll have CV in one of them and CP in the other. So I have ds, which is equal to CV over t dt plus partial p with respect to t at constant v dv equals cp over t dt minus partial b with respect to t at constant p dv. So I can multiply through by t and then successively hold either t constant or p constant or b constant. So let's say we just indicate this, multiply So let's just go ahead and do that. So just as an illustration, let's hold p constant. If I do that, then Guess I've gotta get this thing right. It's a P, sorry about that, everybody get that fixed? So if I hold P constant, then this last term goes out, and I'm gonna end up with okay, so now let me just multiply through by T here. And then I'll divide by dt. But this is, I'm deciding to hold P constant, so that means this is the partial derivative at constant P. So let me rewrite the result here then. I get Cp is equal to Cv plus T times partial P with respect to T at constant V times partial V with respect to T at constant P. And this is the important general result. And there are no assumptions there at all. That is always what the case is going to be. So if I have knowledge of the PVT equation of state, then I can derive this term.